imagine holding a perfectly round ball in your hands, covered in countless tiny hairs, and trying to brush every single one so that none sticks up. You try, twist, and turn it, but no matter how hard you work, there's always at least one hair that refuses to lie flat. It seems impossible, doesn't it? What if I told you that this simple, playful idea actually reveals a profound truth about the universe? A truth that connects mathematics, nature, and even the patterns we see in the world around us. Today, we are going to dive into a fascinating principle called the Hairy Ball Theorem. It might sound whimsical at first, but this theorem uncovers hidden rules that govern everything, from swirling winds in the atmosphere to the magnetic fields around planets. By the end of this journey, you'll see how a seemingly ordinary concept opens a window into deep mathematics, surprising natural phenomena, and the limits that shape our reality. So stay curious, open your mind, and get ready to explore a story where hair, spheres, and the secrets of the universe come together in ways you never imagined. The Hairy Ball Theorem begins with a deceptively simple statement. It is impossible to comb all the hairs on a sphere smoothly without creating at least one point where the hairs stick straight up. In other words, if you imagine a perfectly round ball covered in hair, no matter how carefully you try to brush it, there will always be a cowlick, a swirl, or a tuft that refuses to lie flat. Mathematically, this is expressed by saying that any continuous tangent vector field on an even-dimensional sphere must have at least one zero, a point where the vector is zero. This concept is easy to visualize in 2 dimensions. For instance, consider Earth as a sphere with wind vectors tangent to its surface. The Hairy Ball Theorem implies that there must be at least one point with no horizontal wind, which corresponds to a calm center of a storm, like the eye of a hurricane. The theorem was formally proved using ideas from algebraic topology, which studies the properties of spaces that remain unchanged under continuous deformations. At its core, the theorem connects geometry and topology, showing that local behaviors, such as the orientation of hairs at each point on a sphere, are constrained by global properties of the surface. It is remarkable because it turns an intuitive problem into a precise mathematical statement with far-reaching implications. This theorem also introduces the idea of unavoidable singularities in continuous systems, which appear not just in abstract math, but also in physics, meteorology, and even computer graphics when mapping textures onto spherical surfaces. The simplicity of the idea combined with its broad applications makes the Hairy Ball Theorem a striking example of how deep mathematical truths often lie hidden in seemingly ordinary phenomena. To truly grasp the Hairy Ball Theorem, it helps to imagine a tangible, everyday example, which makes the abstract mathematics much more relatable. Picture a tennis ball covered in tiny hairs, each pointing in some direction along the surface. Your goal is to comb all the hairs so that they lie perfectly flat without any sticking straight up or forming a swirl. No matter how carefully you try, there will always be at least one hair or small cluster of hairs that resists, standing upright or curling into a cowlick. This simple, visual example captures the essence of the theorem and shows why it can be so surprising. The theorem is not merely about hair on a ball, but about the impossibility of creating a continuous, smooth tangent vector field across a surface like a sphere without encountering a zero point. By translating the problem into a familiar scenario, it becomes clear why the restriction exists and why it cannot be circumvented. Beyond visualization, this example also connects to other spheres in nature, such as planetary atmospheres or magnetic fields, where similar swirls or singularities inevitably appear. It emphasizes that the problem is not a result of poor technique or imperfect tools, but a fundamental property of spheres themselves. Visualizing the theorem in this way encourages intuition and curiosity, showing that abstract mathematics often describes patterns and limitations that exist in the real world. The tangible mental image of a hairy ball or a ball of yarn makes the theorem memorable and helps bridge the gap between rigorous mathematical proof and everyday understanding. The Hairy Ball Theorem is deeply rooted in the branch of mathematics known as topology, which studies the properties of shapes and surfaces that remain unchanged under continuous deformations, like stretching or bending, but not tearing or gluing. Topology focuses on the essence of shapes rather than exact measurements, and the Hairy Ball Theorem is a perfect illustration of how global properties of a surface impose restrictions on local behavior. In the case of a sphere, the global structure of its curved surface prevents the existence of a continuous tangent vector field without at least one 0 point, meaning there is always at least one place where a vector, or hair, points straight up. This connection between local and global properties is a central idea in topology, and demonstrates how seemingly simple geometric problems can have deep mathematical explanations. The theorem is an example of how topological invariants, like the Euler characteristic of a surface, govern what is possible on that surface. For a sphere, the Euler characteristic is non-zero, which mathematically guarantees the existence of singularities or zeros in vector fields. This insight has far-reaching consequences, allowing mathematicians and scientists to predict the unavoidable presence of certain phenomena without examining every point individually. Topology, therefore, provides a framework for understanding constraints imposed by the shape of space itself rather than by external forces. The Hairy Ball Theorem highlights how abstract concepts in topology can translate into intuitive realities, offering a bridge between pure mathematics and the physical patterns observed in nature, physics, and even computer modeling. The Hairy Ball Theorem is not just a theoretical curiosity. It has fascinating applications in nature and science, showing that abstract mathematics often mirrors real-world phenomena. One of the most striking examples comes from meteorology, where wind patterns on Earth demonstrate similar behavior to the hairs on a sphere. Because Earth is roughly spherical, horizontal wind vectors across its surface cannot be continuous everywhere without at least one point where the wind is calm or changes direction abruptly. This explains the formation of cyclones and the eye of a hurricane, which represents a natural 0 point in the vector field. In physics, the theorem also appears in studies of magnetic fields around spherical planets or stars, where field lines cannot remain perfectly smooth across the entire surface, inevitably creating singularities. Fluid dynamics provides another example, such as the flow of liquids over spherical objects, where vortices or points of stagnation emerge naturally due to the geometric constraints imposed by the surface. Even in technology, the theorem has relevance in computer graphics and animation, when mapping textures or vector fields onto spherical models, as programmers must account for unavoidable singular points to avoid distortions. These examples illustrate that the Hairy Ball Theorem is more than a mathematical abstraction. It describes inherent limitations in real systems. By connecting the theorem to observable phenomena, it becomes clear how mathematical truths provide insight into the world around us, helping us understand patterns that might otherwise seem mysterious or chaotic, and highlighting the deep link between geometry, topology, and the physical universe. A critical aspect of the Hairy Ball Theorem is that it specifically applies to even-dimensional spheres such as the familiar two-dimensional surface of a ball. This distinction is important because the behavior of vector fields depends on the underlying geometry of the surface. For even-dimensional spheres, like a 2D sphere embedded in three-dimensional space, it is impossible to create a continuous tangent vector field without encountering at least one zero point, where the vector vanishes. In contrast, odd-dimensional spheres do not share this restriction, and continuous, non-vanishing vector fields can exist on them, which highlights the subtle but crucial role that dimensionality plays in topology. Understanding this requirement helps explain why the theorem is both surprising and precise, rather than a vague statement about hairs or vectors. The reason lies in the mathematical concept of the Euler characteristic, a topological invariant that differs for even and odd dimensional spheres. For even-dimensional spheres, the non-zero Euler characteristic guarantees the presence of zeros in any continuous tangent. Vector field. This requirement has implications beyond pure mathematics. It shapes how natural phenomena and physical systems behave on curved surfaces. For example, on the Earth's roughly spherical surface, which is an even-dimensional sphere, the theorem predicts the inevitability of calm points in atmospheric circulation or singularities in ocean currents. Recognizing the dimension-specific nature of the theorem allows mathematicians and scientists to predict and explain why certain configurations are impossible and why singularities must appear, reinforcing the interplay between geometry, topology, and the physical constraints that govern real-world systems. Beyond its mathematical formulation, the Hairy Ball Theorem carries a deeper philosophical and curiosity-driven message, showing that some problems have inherent limitations no matter how cleverly we approach them. It illustrates that certain constraints are not due to a lack of skill or imagination, but are embedded in the very structure of the system itself. This idea resonates across many disciplines, from physics to engineering, where understanding these unavoidable restrictions can guide research and design. For example, in meteorology, the theorem predicts that there will always be calm points or singularities in wind patterns on Earth, and in physics, it informs the behavior of magnetic fields on spherical objects. In computer graphics, it reminds programmers that mapping vectors or textures smoothly onto a sphere will inevitably encounter points of distortion or discontinuity. On a more abstract level, the Hairy Ball Theorem encourages us to appreciate the elegance of mathematics in revealing hidden truths about the world, turning an intuitive observation, like the difficulty of combing a hairy ball, into a precise principle with far-reaching consequences. It also teaches a valuable mindset, that limits exist, but understanding them can lead to creative solutions and deeper insight. Rather than seeing these constraints as obstacles, they can be viewed as opportunities to explore new perspectives, identify patterns, and predict behaviors that might otherwise seem random. The theorem, therefore, bridges the gap between abstract reasoning and practical observation, showing how curiosity-driven exploration of seemingly simple problems can lead to profound understanding and inspiring a sense of wonder about the rules that govern both mathematical spaces and the natural world. In conclusion, the Hairy Ball Theorem is a remarkable example of how abstract mathematics can reveal deep truths about the world around us. From the simple idea of trying to comb all the hairs on a sphere, we uncover connections to topology, physics, meteorology, and even computer graphics. It teaches us that certain limitations are unavoidable, yet understanding these constraints allows us to predict patterns, solve problems creatively, and appreciate the elegant structure of the universe. This theorem reminds us that curiosity and exploration often lead to surprising insights, showing that even the most playful or visual ideas can have profound implications.